that receiver, and it was a very unconventional receiver indeed, was due to this gentleman here. This is Charles Townes. Charles Townes in 1953 had invented the maser, which is the microwave version of the laser. In fact, it came first. This is the ammonia maser 2. It was basically molecular beams experiments that they were doing. But in fact, shortly after doing this, Charles Townes both realized that one might be able to do this with light waves, and so, in fact, his Nobel Prize was both for developing the maser and for his contributions in developing the laser. But he also realized that you could use this maser action to, in fact, amplify weak microwave signals without adding essentially any noise to the signals that you started with. And it was a maser amplifier, not based on this technology, but a ruby rod that was doped and immersed in liquid helium, and that was really developed by Nicholas Bloombergen at Harvard University. That technology was. And by the way, this is Jim Gordon, who then was his graduate student at Columbia University. For many years, he had a wonderful career at Bell Laboratories. So this is, in fact, their data. Now, back in those days, data always came out on a strip chart recorder. A paper was rolled past a pen, which would move back and forth. And so here they're looking at the signal that came from the antenna. Now, they actually added one key piece of instrumentation to this receiver that AT&T had given them, and that was a switch that allowed them to switch this receiver from looking at the signals coming in on the antenna to looking at the microwaves radiated by a black body at a temperature of 4.2 Kelvin. So they could make absolute measurements then of the radio noise signal. So here they're looking at the antenna at a particular place in the sky, and then they switch, and here they're looking at the cold load, that is this black body at 4.2 Kelvin, and then they do some calibrations, and their conclusion was that even though they had pointed the antenna to look in a place in the sky where there were known to be no radio sources, they saw excess radio noise at about 3.3 Kelvin that appeared to be coming in on the antenna. So they then went back and looked at the antenna, and what they found was that the pigeons were roosting inside the antenna. Not a good thing. So they cleaned out the pigeon nests and mopped up the pigeon droppings, and a few copper plates had gotten kind of tarnished in the process, so they repaired them. But nothing that they would do would make this excess noise go away. And not only was there excess noise in this particular direction in the sky, but in fact, wherever they pointed the antenna, where there were no known radio sources, they saw exactly the same amount of excess radio noise. So this really vexed Penzias and Wilson, particularly Arno Penzias. One day, Arno was talking with Professor Burke up at MIT about this excess noise that they were seeing. Now, it would have been very easy for them to simply subtract 3.3 Kelvin from all of their other measurements and get the noise, radio noise, coming from various sources. But the fact that they couldn't understand that was very, very disconcerting. So Professor Burke told Arno Penzias that he should call up Robert Dickey at Princeton University. Robert Dickey had a group that he put together, and one of the people in that group was a theorist named Peoples, and Peoples had this model that as the universe expanded after the Big Bang, once the electrons and protons combined for neutral hydrogen, the radiation that existed at that time, which would have had a very high temperature of several thousand kelvins, would decouple from the matter. And as the universe expands, the radiation cools. And so that at this epoch we are now, in fact, that radiation should be a very low temperature of order a few kelvins. So Arno Penzias called up Robert Dickey. Now, it turns out that one of Robert Dickey's students was someone named David Wilkinson. And David and I worked on a national committee to revitalize physics education in the United States. And I asked him about that phone call. So he said that he only heard the one side of it, the side that what Dickey said, but Dickey was asking him questions to make sure that they had done everything correctly. And then at the end he said, well, okay, they agreed that his people would go up to Crawford Hill, the facility, AT&T facility, where this antenna was mounted, and they would look at the data. And then he hung up his phone and turned to the members of his group that were in his office and said, gentlemen, we've been scooped. Because, in fact, Robert Dickey's entire group was busy looking for this fossil radiation left over from the Big Bang. But they were using a conventional tube amplifier, and according to David Wilkinson, the integrated noise temperature of that system was 2,000 Kelvin rather than the integrated noise temperature of this apparatus, which was 19 Kelvin. So it would have been very difficult for Dickey's group to actually have discovered this fossil radiation, but it was also very difficult for Penzias and Wilson to ignore it when they found it. So let's look at the relevant research strategies. Again, use the best technology available. In this case, the receiver that they'd been given by AT&T was literally state-of-the-art. That was the best receiver there was at that time. But, of course, they'd added this switch which allowed them to make absolute noise measurements. And without that, they certainly would not have made this discovery. Don't reinvent the wheel, borrow if possible. And they borrowed most everything. Look into a region of parameter space that is unexplored. And in fact, these were the first absolute noise measurements, radio noise measurements ever made. And of course, they found something very exciting that had not been anticipated. And then this is very important if you become an experimental scientist. I am an experimentalist. Understand what your instrumentation is measuring. If you don't understand it very thoroughly and you see some subtle behavior that you don't understand, you're very likely to attribute that to the apparatus. It's not working the way I expected it to work. In which case you may well miss a very important discovery. So later on, NASA put up two satellites. The first one was called the Kobe satellite, in which they measured the intensity of this microwave radiation as a function of wavelength. And this red curve is in fact that data, but it is also a perfect black body spectrum. So that showed, in fact, that this was absolutely a black body spectrum, which was expected, but in fact it was very nice to get it. They measured the temperature of this to 1,000th of a degree. So this is a very impressive measurement, but probably the most exciting part of this work, a Kobe satellite, was when they looked at the temperature of this radiation, the black body spectrum, over the sky. They found that it was higher in one direction. These are plotted in what are called polar coordinates. Just imagine that it's the entire sky. A higher temperature in one direction, and in the opposite direction, a lower temperature. And this is because of the motion of the Earth through the local part of the universe. If you get rid of this dipolar effect, what you see is a tremendous blotchiness, and this here is the plane of the Milky Way galaxy. There's a lot of radio noise coming from that. So it's possible, although much harder, to get rid of this, and when you do, you see, in fact, this blotchiness. Now, these variations in temperature are only a few millionths of a Kelvin. Very, very, very small. And so you might wonder whether this is just noise, but of course, what the Kobe satellite people found was that this structure was reproducible, which meant, in fact, it wasn't noise. And so now, in fact, this is a later satellite called WMAP. The W, by the way, is for Wilkinson. David Wilkinson was a member of this team. Sadly, he died before the satellite went up. That's a problem with working with NASA. Not only do you have to